Get her. Get her, Buck. You almost had a doggy battle there. I'm going to get started in 1 minute or so. Okay. I think I'm going to go ahead and get started. First of all, welcome back. I hope you guys had a nice vacation. I will be asking you to what you did on the vacation, during the vacation in the Zoom room, so I look forward to hearing about that. So if you recall, we are talking about experimental physics right now, and what I'm going to be doing is reviewing all the different topics that are on the AP Physics 1 exam, but through the lens of experimental physics. Okay? So let's go ahead and get started with a little review. So today's lesson is going to be about forces, a force experiment. Okay? So let me do a review of forces, some of the common scenarios that you will see. So one of the best examples of using forces is the inclined plane. Okay, so if you are taking the AP Physics 1 exam, then knowing about the inclined plane is, and sort of mastering it as best you can, is really, really important. Okay, so if you have an inclined plane, it looks like this. It makes some angle theta with the horizontal. And then there's a block that is sliding down the plane. Okay? If we were to do a free body diagram of the forces on this box, well, it has three forces. Okay? So one of them is the weight force. So that is mg. The other one is the normal force. The normal force is the force of contact between two surfaces, and it points perpendicular to the incline. Okay? And then, depending on which way this block is sliding, we're going to assume that it is sliding down the incline, in which case friction points tangent to the incline, and in the direction opposite the motion. So we had two types of friction. We had static friction and kinetic friction. And so we're going to assume it's actually sliding. And so this is going to be kinetic friction. All right, kinetic friction meaning that it's actually sliding. All right. So what we then do is we wanted to rotate. So the direction of motion is going to be along parallel to the incline, okay? So what we do is we then rotate the picture, okay, so that the normal force is pointing up and down and the friction force is pointing side to side, okay? Now, how much did I have to rotate the piece of paper? Well, because this angle is theta, I had to rotate the piece of paper by that same angle, okay? So what that means is that mg got rotated by theta degrees, okay? So notice how when I rotate the piece of paper, the weight force is the diagonal force, okay? So I'm going to take that weight force and I'm going to break it up into components. Now this component is opposite the angle, so this is going to be mg sine of theta. That's a little small, but that's mg sine of theta. And this is adjacent to the angle. That's mg cosine of theta. All right. So I can take this diagonal weight force and I can break it up into two components where this component is mg sine of theta and this component is mg cosine of theta. So we want to take diagonal forces and break them up into a vertical force and a horizontal force. Then we still have the normal force, and we still have the friction force. Okay? Now, this block is not jumping off the incline. Okay? So that means that the forces perpendicular to the incline have to balance. So this force has to have the same size as that force. So that means that the normal force is equal to mg cosine of theta, because those two have to balance each other, okay? And then we have a formula for kinetic friction, which is mu sub k times normal. I can't remember if I called normal F sub n or n. Sometimes I do both, so we'll call this F sub n for normal force. This is F sub n. So what that means is that, so this is called the coefficient of kinetic friction. It's a property of the interface between the block and the incline. And so mu sub k times mg cosine of theta is the that is the friction force. So this is mu sub k mg cosine of theta. All right. So now what we do is these two forces cancel out. So what that means is, so I'm going to rotate the piece of paper back to its original orientation. And so to figure out what the acceleration is, we want to do Newton's second law. So this is, the most important equation in all of beginning physics. Probably the most important equation in all of physics. Now, because these two forces are equal and opposite, these two forces are the only ones that are remaining. And they are opposites in opposite directions. So I am going to choose down the incline to be the positive direction and up the incline to be the negative direction. So that means that my net force is the force in the positive direction, mg sine of theta, minus the force in the opposite direction, which is friction, mu sub k, mg cosine of theta. All right. So that is the net force, and that's equal to ma. Every single term has mass, so the mass cancels out, and then I get that the acceleration is equal to g times the quantity sine of theta minus mu sub k cosine of theta. So there are a couple of things that can change. So if the object was sliding up the incline, so if you kicked it, for example, kicked it up the incline, then that would reverse the direction of friction, because friction is always opposite the motion. So that would cause this negative sign to become a positive sign. That's one thing that can happen. Another thing that can happen is it could be frictionless, in which case we would set mu sub k equal to 0. But that is a review of the inclined plane, and I would, if you're taking the AP Physics 1 exam, I would strongly, strongly, strongly suggest that you master the inclined plane, okay? So when I say master the inclined plane, I mean, can you go through these steps without referencing anything else, okay? So, study it, then put the notes aside and try and do the exact same thing that I just did, okay? That's the best way to master that, in my opinion. The other thing that I think is really important for forces, and I'm still just reviewing it because it's been a long time, is what I called quasi-one-dimensional systems. Okay. So for quasi-one-dimensional systems, those are systems that only have two directions. They go forward or they go backwards. All right. So a good example of a quasi-one-dimensional system is you have like a table, and that table has a pulley on it, on the edge, and you have a block, all right, and then you have another block, okay, and so we're going to say that the table is frictionless, so that's another way of saying mu equals 0, and this block has a mass m1, and this block has a mass m2. Now, obviously, what's going to happen is m1 is going to drop, and m2 is going to slide to the right, okay? And so what we did with quasi-one-dimensional systems is we defined a positive direction, which is the direction that the system is going to accelerate. So I'm calling the positive direction sort of the direction where m1 drops, okay? So for m2, the positive direction is to the right, and for m1, the positive direction is down, okay? So the negative direction is if m2 moves to the left, and then m1 goes upward. So then what we did is we drew a free body diagram for each mass. So for m2 has three forces acting on it. It has its weight force, m2g. It has the normal force from the table. Okay, so that was F sub n. And then it has the force from the rope, which is pulling it to the right. So the force from a rope is called tension. Okay, so that is for M2, its free body diagram. For M1, it has only two forces on it. Okay, M1 does not have a normal force because it is not in contact with the ground. Okay, M1 is not in contact with the ground, and so therefore it is okay. It's not going to have a normal force. So all it has is weight force going down. The weight force is different because it is a different sized mass. And then it has tension going up. Okay, so at this point, we are going to write Newton's second law for both M1 and M2. So for M1, Newton's second law, it says net force equals MA. So the net force is positive forces minus negative forces. M1G is in the positive direction because downward is positive for M1. So we have M1G. And then tension is going in the opposite direction, so it is going to be negative, and that equals M1A. All right, so that's Newton's second law for M1. Now for M2, it's a little bit trickier because we have these extra forces, but these extra forces, normal force and weight, because the block isn't moving up and down, they have to be equal in size and they cancel each other out. So these ones are just, we can just ignore these two forces because they're not, they're canceling each other out so that the block only moves sideways. Okay, so really the only force that's moving M2 is the tension of the rope. So the net force is just T, and that equals M2A. So notice how I'm writing Newton's second law for the mass M2. So I have M2A, not M1A, but M2A. So at this point, there are two things that I want to point out. First is that the tension is the same on each end of the rope. Okay, so I don't have to put T1 and T2 because it's the same rope. So the tension is the same throughout at each end of a rope. So that's point number one. And point number two is assuming that the rope is taut. Taut meaning, you know, it doesn't have any slack. Okay. If the rope is taut, then these two tensions or these two accelerations are the same as well. All right. So the acceleration is the same if the rope is taut. So that's another important point. So then what we want to do is we want to solve for the acceleration. So we simply add these two equations together. And notice that here I have minus tension and here I have plus tension. So these two cancel out. The tension cancels out. And on the left-hand side, I have M1G. And on the right-hand side, I have M1 plus M2A. All right. Okay, so and then I divide both sides by m1 plus m2, and I get that this is the acceleration for this particular system. All right, so that's a little review of forces. I hope that made sense. So let's talk about experiments to verify Newton's second law. So actually next week, this is the experiment we're going to do in class. We're going to do an experiments to verify Newton's second law. Okay, I'll just underline the whole thing. So Newton's second law is net force equals ma. All right. So one experiment we could do is we could, and this is the version of the experiment that we're going to do in class, is we can apply a force on an object, and then once we've applied it, while we're applying that force, we observe the resulting acceleration. Okay, so we observe the acceleration that results from that. Okay, and so what we would do is we would then develop a data table of force and acceleration. And we're assuming that this force is the net force. Okay, so you get some data points like this. How do we get the acceleration? Well, just to review what we discussed before the vacation, you might watch something go down a ramp, and you might time how long it takes to go down the ramp, and then use kinematics. So delta x equals 1/2 at squared. All right, so that says that the acceleration is 2 delta x over t squared. So you don't directly measure the acceleration under most circumstances. What you do is you observe the motion, and then you use the motion plus kinematics equations to calculate what the acceleration must have been. Okay. Force is rather easy to measure. So you measure force using a spring scale. So you will see those next week in class. We have these little spring scales, and the amount that the spring scale is stretched is related to the size of the force. Okay, so we use a spring scale to measure force. We use kinematics to determine the acceleration. So you have this data table. Now, what should it look like? Well, I'm going to make a graph of force, net force on the vertical axis, and acceleration on the horizontal axis. Okay. All right. So what should this graph look like if Newton's second law is true? Well, Newton's second law is F equals ma. Net force is on the vertical axis. So, all right. So that means that the net force is acting like y, and then acceleration is on the horizontal axis. So acceleration is acting like x. And that means that mass is acting like the slope. So this graph should look like a straight line. So this is the Newton's second law prediction. And furthermore, we can see that the slope is the mass of the object. All right? The slope is the mass of the object. So that is what Newton's second law predicts should be the relationship between force and acceleration. So if you took some data and you found that this is not a straight line, I don't know, maybe it does something weird like that, then your data would not be consistent with Newton's second law. Okay? Now, Newton's second law has been tested by professional physicists for a long time, and so, probably what's happening if your data does not match Newton's second law, it's because you weren't accounting for something that's impacting your measurement results. Or you might have just found new physics. Okay. So another thing you could do, all right, is you could apply the same force on different sized masses. Apply the same force on different sized masses. And then, once again, you observe the acceleration. That results from that force, okay? So in this case, what you would have is you would have a data table that has the mass of the object, and then the resulting acceleration. Because the force is the same every time, so it's not a variable. And you would get data, okay? So what is the Newton's second law prediction in this case? Well, I can rearrange Newton's second law by dividing both sides by m. All right? So I have net force over m equals acceleration. All right? Force is a constant. So then I would make a graph. So when you make a graph, remember it's the variables on the axes are the two variables that you measure in the experiment. Okay? So you would have acceleration and mass because those are the two things that you dealt with in your experiment. You have different size masses, and then you have an acceleration. So what should this graph look like? Well, we've got acceleration on the vertical axis, so acceleration is acting like y. And then we have m on the horizontal axis. So m is acting like x. But notice how m is in the denominator. Okay, so it's 1 over x. So this graph is basically going to look like y equals a constant over x. And if you've ever plugged that into your graphing calculator before, it looks like this. So that's what a graph of acceleration versus mass should look like. If Newton's second law is true. So this is the Newton's second law prediction. So again, you might not, okay, you might not observe this trend, in which case you either discovered new physics or you did something wrong, one of the two. And it's really tough to distinguish between those two. Actually, in the news right now, you might have heard over spring break that they might have found evidence for a new force of nature. And so, but we don't know, is it actually a new force of nature, or did we just mess up the experiment? So there's going to be a lot of discussion about that in the coming years to try and figure out, is something new happening? Have we discovered new physics, or did we just mess up the experiment? All right. So let me just summarize the basic idea. When testing Newton's second law. So the basic idea when you are testing Newton's second law is you are going to apply Newton's second law to some scenario, and then you're going to calculate what should happen. What should happen. Then you are going to do an experiment with that same scenario. Okay? So you can think of a scenario in your imagination and you can apply Newton's second law to it. Okay? But then when you do an experiment, you actually realize that in the physical world, you do an experiment and you measure what actually happens. Okay? Then what you do is you compare these two outcomes. And they might match or they might not match. All right? So if they match, then that is evidence in support of Newton's second law. And if they don't match, you either found new physics, which is very unlikely at this level, not unlikely if you're a professional physicist, but at the physics that we're learning in this class is very well established. So probably you didn't find new physics, or most likely you messed up somewhere. So, and that mess up could be that your experimental technique was not very good, or it could mean either one of these could be messed up. You could have not accounted for something when you applied Newton's second law, or you could have not done a very good experiment. All right. I'm almost done here, but just let me talk really briefly about the experiment that we're going to do next week. And so what we're going to do is we're going to have a plank. All right. And the plank is at an angle, so we will make an inclined plane. All right. And then we're going to have a little cart. All right. And so the cart is going to want to roll down the incline. All right. But what we're going to do is we're going to put a spring scale behind it. And the spring scale has the ability to measure the force that is pulling the cart down the incline. Okay. So we'll measure the force using the spring scale. Then we'll remove the spring scale and let the cart actually roll down. And then from kinematics, we will determine the acceleration. Okay, so that's how we would get a data point. Then to get another data point, we would change the angle of the incline. Because if the incline is steeper, then there's going to be a bigger force pulling it down the incline. So then we repeat. So we have a bunch of different angles of the incline, which correlates with a bunch of different forces on the cart. And then in each case, we measure the acceleration of the cart down the ramp. Okay? So that's what we'll be doing